In this video, we look at integration by substitution. In the last video, we talked about antidifferentiation using u-substitution. We said it was the chain rule in reverse. We'll review that briefly. And then we'll talk about how that identity that we talked about in the previous video holds when we have a definite integral. Then we'll look at a few examples. In the last video, we did lots of examples of u-substitutions. We're probably only going to do a few examples of integration by substitution, because I think you've already got the idea with the antiderivatives from the last video. Okay, so we said last time that this is the chain rule in reverse, and we did it for a specific example, but I'd just like to show you in general. Remember, the chain rule looks like this. If you're taking the derivative with respect to x of f of g of x, according to the chain rule, we take the derivative of the outside and then we evaluate it at the inside function. And then we multiply by the derivative of the inside. The derivative of the inside is g prime of x. Antidifferentiation by substitution is basically taking us from this side back to that side. So this is what we talked about in the last video. But we didn't do it in abstract in the last video, so let's do it in abstract now. Let's say we've got the integral of f prime of g of x times g prime of x dx. And there might be some extra constants that we can always adjust, as we've seen. Well, if I let u be g of x, then the derivative of u is g prime of x. So the differential of u is g prime of x dx. So this becomes, if I write it in terms of u, f prime of u times du. So if we substitute, oops, there's still an integral there. I replace g of x with u, and g prime of x dx gets replaced by du. Well, if I'm taking the antiderivative of the derivative, what happens in that case is I get the function back. So we get f evaluated at u plus c, and then we say, okay, that's not going to work. We need a final answer in terms of x. So we back substitute. We replace u with g of x, because that's what u was at the very beginning. So we can see through this process that it is that chain rule in reverse. We're identifying that inside function and its derivative, and then it becomes something that we hopefully have a rule for. Now we're taking the antiderivative of a derivative, and the antiderivative of the derivative gives us the function back, and then we back substitute. So that's how that works. Integration by substitution is very similar. Because of the Fundamental Theorem of Calculus, of course. Whenever we're evaluating a definite integral, we start over here. We start with this. But now these represent x values. We're integrating this function and we're saying integrate from x equals a to x equals b. And that could represent area under a curve. Now we start, whenever we're doing integration by substitution for something that looks like this, in exactly the same way. I identify my inside function. I say, hey, look, g of x is inside that f prime, so let's let u be g of x. Then the integrand becomes f prime of u. And du is g prime of x dx. So that can all be replaced by du. All right, that's great. But be careful, you need bounds here. this is a number. This needs to be a number too, but be careful. You can't use these bounds over here. Once I've written my integral entirely in terms of u, these need to be bounds for u, not bounds for x. So in order to get the new bounds for u, we substitute the lower bound for x into here, and we substitute the upper bound for x into this formula, and we substitute that result over here. So we get a new lower bound and a new upper bound. So the new upper bound comes from taking u and evaluating it at the original upper bound, b. So when x equals b, u equals g of b. That's my new upper bound. And then my new lower bound comes from replacing x with a in my formula for u. So when x equals a, u equals g of a. And then we evaluate this definite integral instead. Now when we evaluate this definite integral, this is what happens. We take the antiderivative. Antiderivative of f prime, antiderivative of the derivative, that's the original function. And then we substitute in the lower bound for u and the upper bound for u, and we subtract. And guess what we get? That result over here, that becomes this. F at the upper bound minus f at the lower bound. So it's really f of g of x evaluated at b and evaluated at a, and then we subtract. But we actually don't have to back substitute anymore because you've switched out your bounds for x into bounds for u. It's like you're in a new land. Instead of in the x land, you're in this u land. And in this new universe, you never have to go back to x. You can solve your problems over here. So that's what we're going to do for several problems. Remember, you need to substitute the integrand. All of that needs to be written in terms of u. And these bounds have to be u values. And they're easy to find. You just take the x values over here, and you substitute them into your formula for u. The upper bound for x goes to the upper bound for u. When you use the lower bound for x here, you get the lower bound for u. And then you just antidifferentiate and substitute using the fundamental theorem. Okay, that's the plan. And actually on this, there's some fine print involving domain and range and where these functions are differentiable and all of that. That's in your book. I'm not going to worry about it. But those details are important later if you use these results anywhere else. But for our class, we're just trying to get you to integrate by substitution. So let's practice. Let's say I've got this integral right here. The integral from 0 to 4 of the square root of 2x plus 1 dx. Well, I asked myself, do I have a basic rule for that? I don't, but I see a function nested inside another function. So u sub may be a good choice. So I'll let u equal 2x plus 1, and then I compute du. Derivative of 2x is 2, derivative of 1 is 0. Don't forget to multiply by dx. I'm not worried about the constant, but I ask myself, can I substitute the dx? Yeah, the dx is there. I don't have this 2 though, so I'll divide both sides by 2 or multiply by 1/2, same thing, just to get that dx by itself. So I now know that dx is 1/2 of du. And this is a u under a radical. Okay, so I'm almost ready to write everything in terms of u. The dx is 1/2 du. I'll factor off the 1/2 to the left, factor off the du to the right, and I have a u inside here, but be careful, it's under the radical. That's not just u, it's the square root of u, because u is 2x plus 1. So that's that. But this was a definite integral, so I need new bounds over here. So to get my new bounds, my new upper bound and my new lower bound, I just substitute the values of x that I have here into my formula for u. U was 2 times x plus 1. So I replace x with 4 to get my upper bound. 2 times 4 is 8, plus 1 is 9. Then I substitute in x equals 0 for my lower bound. 2 times 0 plus 1 is 1. So we're integrating from 1 to 9. We have this. We ask ourselves, do we have a rule for that? Almost. We do. We just have to rewrite it first. That's a u to the 1/2 power. So we will rewrite this as 1/2 u to the 1/2 du. U goes from 1 to 9. Okay, then we add 1 to the exponent. 1 plus 1/2 is 3/2. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then you substitute in 1 and 9 and subtract. So that reduces to 1/3. And then we end up with 9 to the 3/2. That's 9 times the square root of 9, minus 1 to the 3/2, which is 1. Square root of 9 is 3. So we have 9 times 3, which is 27. So I have 1/3 of 27 minus 1, so 26 over 3. Okay, so we identify u, compute du, we adjust the constants as necessary. Then we write everything here in terms of u. Every part has to be substituted. So I've got a square root there, it's still there. This is u. dx is 1/2 du. And to get the bounds, I take the bounds for x and I substitute those into the equation for u. I get these two numbers. Now this time, because we've substituted the bounds, we don't have to back substitute. U goes from 1 to 9. So you antidifferentiate here, and then you evaluate from u equals 1 to u equals 9 using the fundamental theorem, plug in 9, plug in 1, and subtract, and that's your answer. No need to back substitute with definite integrals. Excuse me. Okay, let's do one more, or actually, let's do 2 more. So I have the integral from 0 to 1 of e to the x plus 1 over e to the x plus x dx. Now that one looks complicated. It looks like, oh my goodness, I don't see any parentheses. Now you might be thinking that the inside function is x because there's an x inside the e to the x function, but there's not enough going on with that. If u is equal to x, then du equals dx, and what you end up doing is just replacing all the x's with u's and nothing changes. It's just the same problem in a different form. We want the same problem in a different form, but we want a form that actually gets us closer to finding the answer. So if we don't see an obvious inside function, if we have a fraction like this, so you've got some function divided by another function, often, it's not always the case, but often, u is the denominator. You should always just try it. If you don't see another obvious inside function, try u equals the denominator. It might work. And it turns out to work in this case. If u is e to the x plus x, du is the derivative of that. The derivative of e to the x is e to the x. Derivative of x is 1. And I misspoke. Du is the derivative of that times dx. Don't forget your dx. Okay, and then I ask myself, do I have an e to the x plus 1 dx up there? And I do. Got a u in the denominator, and there's a du in the numerator. Okay. Now some students have trouble substituting this because they want to say that this is u times du. It's not. That u is in the denominator. So you want to think of that as a 1 over u times du. Because if I wrote this as itself over 1 and multiplied straight across, I'd get du over u, which is exactly what I have there. But I don't want the du in the numerator, really. I want it off to the side just to tell me to integrate with respect to u. Okay, I can take the antiderivative of that, no problem, but it was a definite integral, so I need new bounds. So I need a new upper bound, or upper limit of integration, and I need a new lower bound, or lower limit of integration. So I evaluate my function u, that's e to the x plus x. I evaluate it at 1, and I evaluate it at 0. E to the first plus 1 is just e plus 1. So that's my new upper bound. My new lower bound is e to the 0 plus 0. E to the 0 is 1, so I've got 1 plus 0, which is 1. All right. Now that's a definite integral in terms of u that I can evaluate. The antiderivative of 1 over u is natural log of the absolute value of u. I would normally say plus c, but it's a definite integral. So we're going to integrate from u equals 1 to u equals e plus 1. So we get natural log of the absolute value of e plus 1. Since e plus 1 is positive, no absolute value bars are needed. Then we subtract natural log of the absolute value of 1, which is just 1, and natural log of 1 happens to be 0 because e to the 0 is 1. So we get natural log of e plus 1. And even though it doesn't look like it, that's actually a number. This is natural log of about 2.7 plus 1. So this is natural log of about 3.7. If we substitute that, or if we type that into our calculator and hit equals, it will give us a numerical approximation of that. So that is an area under the curve between this function and the x-axis from x equals 0 to x equals 1. One last one. Just another one that involves e. I don't know why I chose a bunch of problems involving e this time, but I did. Okay. First of all, ask yourself, do I have a rule for that? It's a product, so I don't. So then I need to identify an inside function. I say, what's nested inside another function? Well, that negative x squared is. So that may be my u. I'm never really sure until I take du. So I identify u, compute du. The derivative of negative x squared is negative 2x. Don't forget to multiply by dx. And then I compare this to what I have up here. I have an x dx, so the u sub's going to work. That's great. But I'd really like this to be a 4x dx. To make this a 4, I'll multiply both sides by negative 2. So we'll have negative 2 du equals 4x dx. So that's negative 2 du. So we've got the integral of this. 4x dx is negative 2 times du. This is e raised to the u power. That's great. So we've substituted everything. That has been replaced by negative 2 du. That has been replaced by e to the u. The only thing we need is bounds. So we will find the new upper bound and the new lower bound and subtract. So I replace x with 2, I replace x with 0, and I subtract, so I get negative 4 and 0. All right, so those are my bounds. Now we just antidifferentiate, bring the negative 2 down, the antiderivative of e to the u is e to the u, substitute in u equals 0 and u equals negative 4 and subtract. So I get negative 2 times e to the negative 4 minus e to the 0. E to the 0 is 1. If you want, you could make that a positive 2 and distribute the negative through here. That's probably what they did if you checked your answer in the back of the book. They'd make that coefficient positive and then flip that. If you distribute the negative through here and change the order, that's exactly equal to that. Okay. So this is just like the antidifferentiation by substitution. The only difference is if you have bounds, you need bounds for u. In order for these truly to be equal to each other, this is an area under the curve. This is an area for starting from x equals 0 and going to x equals 2. If this is going to equal this, I need to write this area under this curve is equal to this area under this curve. Like these are two related areas. The only way those areas are the same is if we change the bounds, because these are x values. Once I write an integral in terms of u, I need u values. And then we're saying, well, this area happens to be the same as this area, or this net area happens to be the same as that net area. And the net area between this function and the x-axis on the interval from 0 to 2 happens to be this. And the net area between this function and the u-axis on the interval from 0 to -4 is this.